Hello class, in this video we're going to go over OWL 2 to make sure that we understand some of the questions. I'm only going to run through one question per piece just to kind of save up on some time, but I will be doing some tutoring later on this week so that way you guys can have a little extra additional help. All right, so one of the questions is going to ask about Lewis dot structures. The Lewis dot structure, if you see one circle or one dot, that tells you how many valence electrons are present. Remember, valence electrons are the electrons in the outermost shell. And all of these electrons or all of these atoms are trying to be like the noble gas and have their electrons, their shells filled. So in this circumstance here, we only have one valence electron, and the number of valence electrons will match the group that they belong to. So this guy here is in group 1. Now, because this guy only has one valence electron, it's actually easier to get rid of that electron than it is to try to grab 7 more. So because of the fact that it's going to donate an electron, it's actually going to gain a charge of +1 because now we have more protons than we do electrons. And then what it's going to ask is it wants us to see if this particular atom or this particular element was in period 5, what would their electron configuration now be if they donated one of their electrons? So we have to go to our periodic table. If they're in period 5 and they're in group 1A, they're more than likely rubidium. And the closest noble gas, if this guy was to lose an electron, would be krypton. So we're going to type in krypton here. And the symbol for this ion would be rubidium. And then we're going to make sure that we show a +1 charge. Submit our answer, and then we're good to go. All right, next question, and I'm going to go out of order a little bit just because I want to do all the naming together and writing the formulas together. We're going to talk about how to name binary compounds. So this is going to be between a metal and a nonmetal. So you write the metal, you write the stem of the nonmetal, and you end in "ide." So for instance, Al is aluminum, Br is bromine. We're going to write aluminum bromide. Make sure I spell this correctly. Aluminium. All right, next one is magnesium and oxygen. So this will be magnesium oxide. And then we have Na, which is sodium. And then we have S for sulfur. This would be sodium sulfide. And in case you're not sure of a particular element, you can actually go to your periodic table and it will tell you the name. So we'll submit our answer and we're good to go. Now, when it comes to writing these formulas really quickly, I'm going to, like I said, I'm going to skip around just a little bit. But for this guy here, what we're going to do is we're going to try to actually complete the table. So what they do is they show you the metal and they show you the nonmetal, and we need to put this together. So if we had manganese and then oxygen, this would become manganese oxide. Now, because their charges are the same, what's going to end up happening here is we want to get an overall charge of 0. So we have Nm plus 2 and oxygen -2. Their overall charge is going to be 0. So we're just going to write it like this for manganese oxide. Now, for this guy here, if we look at the zinc iodide, we're going to notice that they're not the same. Their charges are different. Zinc has a charge of +2, iodine has a charge of -1. Now what's going to happen is in order to balance this guy out, we have to have 2 iodine for 1 zinc. So to keep this in mind, think about doing a cross. Now that -1 charge is going to be like a little subscript down below for zinc. But because it's just 1, we just write Zn. But for iodine, now that 2 is going to come to the bottom. So we're saying that we need 2 iodine atoms for 1 zinc. So this is Zn, I, little subscript 2. And then we have our cobalt sulfide. Same thing here. This is a +3 charge. This guy has a -2 charge. They're not the same, so we're going to have to do our cross. So we're going to need 2 cobalt and 3 sulfide in order to balance this guy out and have an overall charge of 0. So this is CO2, S3. Submit our answer, and we're good to go. All right, next what I'm going to do is I'm going to skip around. I'm going to skip to number 7, which is naming covalent bonds or covalent compounds. And what we're going to see is that these are between 2 nonmetals. So our naming is going to be a little bit different. So when we look at these guys here, we want to figure out if we have a metal and nonmetal or if we have 2 nonmetals. In this circumstance here, when we deal with 2 nonmetals, we actually care about their prefixes because they don't have charges. They're sharing the pair of electrons because it's a covalent bond, but we have to care about their prefixes. So I do want you to feel familiar with these prefixes. You're going to see them quite a bit, and we want to make sure that we can name these covalent compounds. So for the first guy here, we have phosphorus and we have 3 iodine. So what's going to happen is because there isn't any subscripts below for phosphorus, for the first guy, we can just write phosphorus. Now, if there were 2 phosphorus, we would have to write diphosphorus. But because there's only 1, we can write phosphorus. But then what we have to do is we have to show how many iodine we have. And what we would say is phosphorus tri for 3 iodine. Next, we have silicon dioxide. And then finally, we have sulfur trioxide. And so we write it in this sort of circumstance here. Let's do one more just to make sure we can practice this. All right, so this way we're going to see it kind of opposite. They're going to give us the name and we have to come up with chemical compound. So we have sulfur, and then oxide is oxygen, and then di tells us that we have 2. For carbon tetrabromide, again, we just have carbon. And then for bromide, tetra means 4. And then finally, we have disulfur. So that tells us that we have 2 sulfur. So we get to write S2. And then it says decafluoride. And deca means 10. So this would be S2F10. All right, so I hope that makes a little bit of sense. Next, what we're going to do is we're going to practice writing ionic compounds. So these are going to be where we actually have a polyatomic ion, which means it has more than 1 atom within the ion itself. So these guys are going to be a little bit tricky. And basically what I want you guys to do is I don't want you guys to memorize them necessarily, but I want you to be familiar with how to name them and how we would put them together. So for this first question, we have K, which is potassium. And then we have this OH. OH stands for hydroxide. So we would put hydroxide in here. Next, what we're going to see is we have this KHCO3. This stands for potassium, and H3O3 is bicarbonate. And like I said, you have a little list if you go through your sort of preparation and you can see them. You can also go to your chapter 5 slides and you should be able to see some of these compounds as well. And then finally, we have AlCN3. We only care about just naming the metal and then the polyatomic ion. So in this circumstance, we have aluminum. And I cannot spell aluminum. And then CN stands for cyanide. Submit our answer, and we're good to go. Now you may see it where we have to actually write the compound out in this format, or you may see it sort of written like in this format. Let's do a couple more. So we have magnesium. Magnesium for Mg, and then SO3 is going to be that we have sulfur sulfite. Magnesium sulfite. Again, SO3 we would get from the polyatomic ion chart, and then we'd be able to name it. All right, Al is aluminum. And then CO3 is carbonate. So that's all we have to write. We don't care about the charges at this moment in time. All right, and then we have calcium for Ca, and then NO2 is nitrite. Go ahead and answer that, and we're good to go. All right, couple more things I want to do really quickly, and then we'll go back into our order. Is I want to go to talking about balancing chemical equations. So like I said, conservation of mass. Matter is neither created nor destroyed, so we have to make sure that we have equal amounts of atoms on each side, the reactant and the product side. So for here, we want to balance out our equation. So what I like to do, if you will, is sort of just make a line. These are our reactants. We see that arrow to tell us yield, and then we have our products. So right now I have 1 carbon. I have 1 oxygen for the CO, but then I also have 1 over here for water. So I have 2 oxygen right now. And then I have 2 hydrogen. On my product side, I have 1 carbon. I have 2 oxygen, and I have 2 hydrogen. Because of the fact that this is balanced, we're actually good to go. I think what they're going to want us to do is just add some 1s to make sure that this is correct. Normally we would omit the 1, but just to make sure that we've answered this efficiently, I think we're good to go. All right, now they won't always be this simple. So let's try another one really quickly. All right, again, same thing here, draw our line. On the reactant side, I have 2 hydrogen. For iodine, I have 2 on the reactant side. On the product side, I just have 1 of each. Now, again, I can't just write a little subscript down here because that actually changes our compound. But what I can do is I can throw a coefficient out in front. I need to get 2 of hydrogen and 2 of iodine. I can stick a 2 out in front. And again, normally we would omit the 1s, but because of OWL being funny, we're just going to add them in, submit our answer, and we're good to go. All right, so now we can go back up to our other questions really quickly. Okay, so we talked about what to do for Lewis dot structure. We talked about writing the binary compounds. Next, let's do formula weight. So formula weight is taking into account how many ions are present. So for instance, when we talk about the atomic weight, we're just going to pull this from the periodic table of elements. If you look for lead, lead is Pb, and it's plumbum, which is the Greek terminology, and it comes from having, like, again, lead pipes. Think of like plumber. So let's get Pb. Pb is going to be 207.2 for its mass. So it's 207.2. And again, they can say atomic weight or atomic mass. If we go to look at iodine, again, hit the periodic table, it's going to be this 126.90. But now we have to care about how many ions we have. Now, again, we're going to put this into a compound form. So Pb plus 2, I minus 1. We're going to do our cross, and we're going to have 1 lead for 2 iodine. So the number of ions for lead would be 1. The number of ions for iodine would be 2. Now, all you have to do is multiply for getting the actual weight of the ions. For lead, this is just going to be 207.2. But now we have to care about the mass for when we're dealing with the ions now. And so now what's going to happen here is we have to take into account that we have 126.9 times 2. So let me get out my calculator here. 126.9 times 2. This comes out to be 253.8. And now we have to actually add these numbers together. And we end up with 461 AMU total. Submit our answer, and we're good to go. So with the number of ions, be careful to make sure you're doing your cross. That way we can figure out how many of each ion we have present. And then from there, again, we're just going to calculate the weights by taking the atomic weight times the number of ions. Total up and add together the weight of the ions, and you'll have your formula weight. All right, next we're going to be dealing with electronegativity. So this is going to be the affinity that an atom has for electrons. And how the trend works is that it increases as we go across, it decreases as we go down. So fluoride would be the greatest electronegativity. This francium would be the least. So what we want to do is we want to make sure we put them in order from increasing electronegativity. So we're going to start with the smallest and work our way up to the most electronegative. And they give us the guys that they want us to look at. So they want us to look at beryllium first. And beryllium, we're going to find, it should be Be. So it's right here. Then we have boron, we have lithium, and we have carbon. So what this is showing you is the trend that we're going across. And as we go across, we increase in our electronegativity. So lithium would be the smallest. Then we would have our beryllium. Then we would have boron. And then finally we would have carbon. And then we can go submit our answer and we are good to go. All right, practice just another one really quickly to make sure this makes sense. Again, we want to order in increasing electronegativity. So it'll increase as we go across, it decreases as we go down. So I'm going to say increase as we go up, decrease as we go down. So now we're looking at oxygen, selenium, sulfur, and this beryllium. Again, as we move our way down, it decreases. So beryllium, or tellurium, I actually believe is how you properly announce it, would be the smallest. Then we would have our selenium. We would have our sulfur. And then finally, we'd have oxygen. Because remember, the fluoride is going to be the most electronegative. Francium would be the least electronegative. Submit our answer, and we're good to go. All right, next little piece that we're going to see is it's going to ask us about polar and non-polar molecules. Polar means it has an increase in electronegativity, and therefore it's going to be where we see kind of a plus, a slightly positive, slightly negative charge on one of the atoms. Versus non-polar means that they share them pretty equally. So in this case here, if we're to look at beryllium chloride, because the chloride's in the middle, what's going to end up happening is, yes, it's going to have a slightly electronegative charge, but because we have these berylliums on both ends, kind of keeping it in check, this is going to be a non-polar molecule. All right, down here, if we were to look at this NOCl, what's going to end up happening here is the oxygen is going to have really a very strong electronegativity. So this is going to be polar. And then down here, if we were to look at this SO2Cl2, what it's showing us is that we have the sulfur in the middle, and then we have 2 oxygen and 2 chlorine. What's going to end up happening here is, again, same thing that kind of what we've seen before, because there's sort of this affinity for electrons sort of pulling in opposite directions, they're going to kind of balance each other out. So this is going to end up being nonpolar. Go to submit our answer. But actually, this is going to be polar. And then we're going to see our answer. The reason that the Lewis dot structure below is considered to be polar, and I misspoke before, is that it's not symmetrical. So had it been SO4 all the way around, it would be symmetrical. And then, or if it was like SCl4 all the way around, it'd be symmetrical. But because they're not, again, oxygen ends up having that greater affinity. So this guy ends up being polar. Let's go ahead and practice another one really quickly. All right, so CO2, this is going to be nonpolar because again, although the oxygen has great electronegativity, that symmetrical component to both carbons being on each side, they're kind of pulling each other and kind of washing away that charge. SCl2, whether or not this is going to be polar or nonpolar, because of its shape, the chlorine is actually going to have this bent shape associated with it. And it does have a greater electronegativity than sulfur. So this will be polar. But for this guy here, this SbF3, again, because of its structure, those fluorines are sort of pulling on that Sb here, this antimony, and it's kind of going to wash away that charge. So this will be nonpolar. Am I wrong again?